In a style that's not been done before, this video will cover what a force is, the conservation of energy, the relationship between potential energy and force, a brief tutorial on differentiation calculus, and finally we're going to prove the conservation of energy using maths. I've broken the video down as much as I can. Every question is valid, so if there's any questions you have, leave it in the comment and I'll get back to you as soon as I can. Also, if you haven't already, subscribe and take a look at the Pretty Pouch Company for great gifts for a great price. Thanks to them, I got the best Mother's Day gift I could possibly give my mum. You know, after me. Forces are everywhere. So what is a force? A force is anything that will change the motion of an object when not resisted. It's given by Newton's formula. Force is equal to mass times acceleration. There we had 4 units of mass. Suppose we have 2 units of acceleration. Then all 4 mass units would accelerate at the same time. If you counted the acceleration arrows, you'd get 8. 4 units of masses accelerating at 2 units of acceleration gives you 8 units of force. This is what the multiply symbol does. It says the entire mass, which is the amount of mass something's made out of, accelerates, which is the ability to gain or lose velocity. So the formula eloquently states that the force is when matter gains or loses velocity. In the previous video, you found out that to define the state of a particle, you need to know its position and velocity. This is built into the force equals mass times acceleration formula, because acceleration is a changing velocity, and to know the velocity of an object, you need to know how its position was at one point and how it changed in time to the next. Conservation laws are seen a lot in physics, the conservation of energy being one of them. It's used in the studies of electrodynamics, electromagnetic radiation, relativity, and even quantum mechanics. So what is conservation of energy? We need to understand energy first. There are 2 types of energy, kinetic energy and potential energy. The total of these give the total energy of a system. Let's prove the conservation of energy. To do that, we need to show that it doesn't change with time. This is the relationship between a force and potential energy. Let's break down this formula. Capital U represents potential energy. The thing in the brackets is known as an argument. It says that the potential energy changes based on where it is in the X position and Y position. We could also have Z in here, but to keep things simple, we kept it to 2 dimensions. The triangle represents the potential energy is changing. Don't worry if you don't quite get this formula. We're going to do a practical demonstration to help you visualize it now. Here's the formula. Imagine there's a ball sitting on the terrain on the background. We know that the gravitational potential energy of the ball depends on the position of the ball in the gravitational field. As a reference point, let's say U, the gravitational potential energy of the ball, is 0 based on where it is currently. As the ball rises, its position changes and so does its gravitational potential energy. While the potential energy is increasing or decreasing, the force associated with gravity is acting in the opposite direction. So for example, as the potential energy increases, the height of the ball increases too, but the force of gravity is trying to pull it back down. And this is why there's a negative symbol in the formula. Think of negative as being opposite to something else. It's like 2 opposite charges, positive and negative. It tells us no information except for that it's an opposite charge. In the same way, the negative symbol in the formula just says that the force acts in the opposite direction to the increase in potential energy. To prove conservation of energy, we need to know some brief calculus. Here's what you need to know. Suppose that we're interested in a physical property. Let's call it Y. Just like the above formula, where force depended on the change in potential energy, let's imagine that Y changes with a variable called X. So Y changes based on X. X is known as the argument and Y is known as the function. Function basically means output, and Y is an output of X. If we want to know how Y changes based on X, we call that dy by dx. dy by dx is not equal to x to the power 1. By the way, x to the power 1 and x are the same thing. I just wrote it in this form so it'd be easier to demonstrate what I'm trying to show. To find dy by dx, you take the power and multiply it to the term, and then reduce the power by 1. Anything to the power of 0 is just 1. so dy by dx is equal to 1. What about this example? The same rule applies. Multiply the power to the term and subtract 1 from the power. Now we're ready to prove the conservation of energy. Remember, the total energy of a system, which I'm calling E, is equal to the kinetic energy, which I'm calling T, plus the potential energy, which I'm keeping as U. Kinetic energy is equal to half times mass times velocity squared. To prove the conservation of energy, we have to prove that the total energy doesn't change with time. So we need to differentiate total energy with respect to time. How the energy changes with time should be equal to 0, since there is no change. To do this, we differentiate the kinetic energy and potential energy with respect to time, and adding them up should equal to 0, proving that total energy is conserved. Let's see how the kinetic energy changes with time. The half is a constant, which doesn't change with time. The mass is also a constant that doesn't change with time. The only thing that will change with time is velocity. So the kinetic energy will change with time because the kinetic energy will change with velocity, and velocity changes with time. Let's work out dt by dv using the calculus we learned earlier. T is the output or function and v is the argument. Multiplying the term by 2 and dropping the power by 1 gives dt by dv to be equal to mv. dv by dt, or how the velocity changes with time, is also known as acceleration. So how the kinetic energy changes with time is the mass times the velocity times acceleration. The order in which we multiply in does not matter, and that's known as the associative law. So we can rearrange mva into ma times v. We know from earlier in the video that force is equal to mass times acceleration, so ma here will equal force, and the v stays the same, so it's force times velocity is how the kinetic energy changes with time. How does potential energy change with time? Well, potential energy changes with position, and position changes with time. A position changing with time is also known as velocity. Remember, a force is a negative change in potential energy with respect to position. So how the potential energy changes with position is also the negative force. Now then, the total energy changes with time because the kinetic energy changes with time, plus the potential energy changes with time. Adding these two quantities together gives you 0, and therefore the change in total energy with respect to time is 0, and energy is conserved.